Hi students, now we are going to derive an expression for the kinetic energy in pure rolling motion. So what is rolling motion? We have just studied. It is a combination of what? It is a combination of translatory motion and rotational motion. So the kinetic energy in rolling motion must be equal to the kinetic energy in translatory motion added with the kinetic energy of the body in rotational motion. So I will write the expression that the total kinetic energy in rolling motion is equal to the kinetic energy in translatory motion plus kinetic energy in rotational motion. Okay, now here when we speak of rotational motion, you can see here this is the wheel. When the wheel is in rotation, if you take this is the axis of rotation, about this center of mass, the wheel will have a moment of inertia. Understand? So all the particles between the point of contact and the center of the wheel will have two velocities, that is translational velocity and rotational velocity, and we have to consider the axis passing through the center or center of mass. Another chance, if you want to analyze its rotation about the point of contact. So about the point of contact you have to fix the axis. Okay, about the point of contact you have to fix the axis. Already we have studied, my dear students, at the point of contact the magnitude of the rotational velocity and the translational velocity are equal in magnitude and opposite in direction. So the resultant velocity of all the particles on the rim at the point of contact will be equal to 0. So the particles at the point of contact cannot have translational kinetic energy. The translational kinetic energy at the point of contact is equal to 0. Why? Because the particles are momentarily at rest, but the wheel is rotating about an axis passing through the point of contact. Okay, rotational motion it will be having. So it will have only rotational kinetic energy. So there are two possibilities. One is I will find the total kinetic energy of rolling motion in case 1, okay, with reference to the center of mass, So with reference to the center of mass, each and every particle will have what? Two kinetic energies. So the total kinetic energy is now equal to the translational kinetic energy, okay? Translational kinetic energy plus kinetic energy of rotation. So this is equal to, what is the translational kinetic energy? If the body is having a mass capital M and its radius is r, then we can write this is half into m into v square center of mass, because all the particles they have translatory motion as well as rotational motion, is it not? So the velocity of translational motion is equal to the velocity of the center of mass. So it is v cm square plus half into I omega square, where I cm is the moment of inertia of this wheel about the point with reference to the center of mass we have mentioned, is it not? So the axis is passing through the center of mass. So here I cm into omega square. But we know that V center of mass is equal to V translation, that is equal to R into omega. R omega is equal to what? Velocity of center of mass divided by the radius. Is it not that? Moreover, here I cm we have to substitute, is it not? So this is equal to half m into v square cm plus half into ICM is m into k square, where k is the radius of gyration. Understand? So instead of I center of mass, I have substituted I mk square. That is I is equal to mk square into omega square. What is omega equal to? VCm by R. So this is a VCm square by R square. Because it is omega square, is it not? So VCm by R the whole square is VCm square by R square. Okay, now this is equal to half m V square, okay, Cm plus, here half term is there, here m is available, okay, into here V square Cm I will write first, V square center of mass into k square by R square. So this is k square by R square. Understand? So this is now equal to half m V square, half m V square Cm into 1 plus k square by R square. So this is the expression 1. Which point we have taken as a reference, which is the center of mass. So about the center of mass, what is the moment of inertia of this wheel is ICM. Understand? And we have added the translatory kinetic energy plus rotational kinetic energy, and that is the kinetic energy of the pure rolling motion. And we have derived the expression what rolling motion's kinetic energy is equal to half m v square Cm into 1 plus k square by R square, where k is the radius of gyration. Okay, this is with reference to which point? So if this is the wheel and if this is the axis, okay, so this is the axis of rotation which is passing through the center of mass, and this is what the moment of inertia. Okay, now the second case I will consider the second case with reference to the point of contact. Okay, with reference to the point of contact. So in this case, at the point of contact, all the particles touching the surface will have net velocity 0, because V rotation is equal to V center of mass. They are equal in magnitude and opposite in direction. Resultant velocity is equal to 0. Therefore, a translational kinetic energy. So in this case, kinetic energy, translatory kinetic energy is equal to 0. So it has only rotational kinetic energy. Therefore, the total kinetic energy is equal to its kinetic energy of rotational motion only. Okay. Also, rotation about which axis? Axis passing through the point of contact. This time the axis is not passing through the center of mass. We have to consider an axis passing through which point? The point of contact. Is it also parallel to the other axis which is passing through the center now? Like this we have to imagine. Understand? So in this case, in the second case, now the wheel will be like this. Okay. So this is the axis passing through the center. Now we are referring to this axis passing through the point of contact. So this is moment of inertia about the center of mass, and this is the point of contact. And here the moment of inertia is taking a new symbol I0. And the distance between these two axes is equal to the radius of the circle. Now we are going to use what? Parallel axis theorem. Very simple. Okay. So this is now equal to what? Half into I0 into omega square. Previously we used I center of mass, is it not? Because the axis was passing through the center of mass. This time the axis is passing through what? The point of contact we have to consider. So I0 into omega square. So using parallel axis theorem, okay, using parallel axis theorem, we can write that I0 is equal to I center of mass plus m into the distance square. So the distance between the two parallel axes is equal to the radius. So this is mass into r square, radius square. Okay. And I center of mass already we have derived, is it not? So I half into that is a ICM is equal to mk square. So this is equal to mk square plus mr square. Okay, mk square plus mr square. So that we have to substitute here. Therefore, the kinetic energy in rolling motion is equal to half into I naught into omega square. So for that, half into mk square plus mr square in place of I naught into omega square. In place of omega square, what I have to substitute, children? VCM by R. So VCM by R the whole square. So this is now equal to half into mk square plus mr square into v square cm divided by r square. Okay. So now half I will take as a common factor. So this is now equal to, that is total kinetic energy is equal to half mk square into v square by r square. So half into mk square into vcm square by r square plus half mr square into, so this is half mr square into v square cm divided by r square. Okay. So here this r square and r square get cancelled. Now I take the common factor. So this is equal to half into m into v square cm into here k square by r square. So k square by r square plus 1. Therefore the total kinetic energy of rolling motion is equal to half into m v square cm into 1 plus k square by r square. So this is the expression for the rolling motion, kinetic energy due to rolling motion. So here also we are getting the same, you see, with reference to the center of mass also we get the same expression, half m v square into 1 plus k square by r square, and with reference to the point of contact also we get the same expression. Understand? So from this we come to know that the kinetic energy in rolling motion will be constant. Understand? Irrespective of the reference point, be it the center of mass or the point of contact. I hope you must have understood well. Fine.